Okay, so welcome to the Friday, now Thursday, theoretical astrophysics seminar. It's a real pleasure to have Professor Daniel Schaerer here as a speaker from the University and Observatory of Geneva. So Daniel has done really important work in many areas of galaxy evolution and cosmic star formation history of galaxies across a long span of cosmic time. Indeed, he has been one of the pioneers of observing high-redshift galaxies in all possible wavelengths. His focus has been indeed in understanding the early stages of galaxy formation evolution and how star formation happens at very high redshift in starbursts as well as in other type of star-forming galaxies. He has used gravitational lensing to probe the high redshift phase of galaxy and star formation. He has used a variety of instruments in all possible wavelengths, and now I think he's also going, like many people in the field, to the JWST domain. He has done fundamental work in understanding the effect of galaxies at high redshift on the reionization of the universe. So Lyman-alpha galaxies and Lyman-alpha, Lyman break and Lyman-alpha emitters. Today we will talk about Lyman-alpha emitters, I believe. And also he has tried to find evidence for population 3 stars and measure also the ionizing radiation from galaxies, which is also one of the topics of today. We have been involved in collaborations for a long time. Daniel has been the leading person, the main PI of the Synergia Star Formation, Star Force, was the acronym, which has been, I think, that the first big activity Swiss-wide to connect people working on galaxy evolution and star formation. And this went on for 2 cycles, right? Because it was Star Form 1 and Star Form 2. So we have been working together on this for more than 6 years. And now we are also collaborating, and many of us are collaborating with Daniel's group and other groups in Geneva in the AstroSignal Synergia project. So I think it's really a pleasure to have. It's a pity that we cannot have him here for longer, given the many interactions that we have had and we are having now. And let me just give you a brief description of his career. So he got his PhD in 1995 at the University of Geneva, previously studying at ETH for the undergrad studies. And then after his PhD, he went to the US. So he was a postdoc at the Space Telescope Institute, Johns Hopkins University, and he stayed here for some years. Then he came back to Europe, and he was a postdoc at the observatory in Toulouse. And then in 1999, he became a researcher, a CNRS researcher, also in Toulouse, in what is now the IRAP Institute, the Institute for Astrophysics and Planetology. After that, he came back to Switzerland with an SNL professorship. And then since 2008, he has been a professor, a tenure professor at the University of Geneva and the observatory. And so without any further discussion, I will let you start your talk, which is empirical and physical properties of Lyman Continuum.
Yes, thank you very much, Lucio. Thank you, everyone, for being here. So I'm glad to start this seminar now after these initial difficulties and to be here and talk to you about work we've done during the last 6 years or so, mostly on what we call Lyman Continuum emitters, which are galaxies which emit ionizing photons, which can escape them and potentially ionize the intergalactic medium. So I will structure my talk in the following way. I'll give you a quick overview of what the questions are, what we're after, and then show you a little bit the progress we've made since 2016, where there has been really a change after discoveries we made with HST. And I'll give you then an overview of what we know right now about these analogs of cosmic reionization, so what we know about them, and also questions, and then, of course, a little bit where we're going next. So, of course, what we're talking about and the overall goal we're trying to study is, to understand the early phases of the universe. I think you all know this, does not need much motivation, but basically we're the main question, or one of the main questions is, to understand the transition during the formation between the formation of the first stars to roughly 1 gigayear after the Big Bang, where the intergalactic medium is reionized. And of course, the questions are, we have of course, insights so far, from simulations for which you are, of course, professionals, and you are doing great work on these aspects here. Sorry for showing a simulation which does not come from Zurich. But I know that you're also doing these things. It's just for illustration and probably don't need to comment on it. So you all know how these things happen and how in the simulations, and I think they are very important to guide us and, to give us conceptual pictures and a way to structure our mind, and also to start from there on to ask questions. Can we observe some of these things in real life, and is the universe behaving like you're simulating, and vice versa, of course, to give you simulators constraints on from real life observations. And so, of course, some of the constraints we know, you have probably seen these kind of pictures. We have some idea about the average evolution of the neutral fraction of hydrogen, which is shown here as a function of cosmic time, or as a function of redshift here from different observations, including also from Planck. So we have some rough idea of the timeline. And as I mentioned, basically this timeline corresponds to, roughly up to 1 gigayear after the Big Bang, which is here when most of the neutral gas in the intergalactic medium disappears. So the universe is essentially, the intergalactic medium is essentially ionized or reionized. Now, of course, one of the questions about this epoch is to know, what are the sources of these UV photons which must exist to reionize the intergalactic medium. And basically, we can say that we can come up with two categories. Either it's stars, so it's galaxies which contain stars, or it's quasars. But there could be also other exotic sources, some of which have been discussed in the literature, and I just list some of them here. And I have no time to go into this debate in detail. But most people think, and I will show you some evidence for that, is that actually galaxies are the main drivers of cosmic reionization. And if that's true, or if we study galaxies, within there are other questions. What galaxies are the dominant emitters of Lyman Continuum photons? Is it low mass galaxies? Is it massive galaxies? What type of, in which phase, and so on. We can also ask the question more physically, how do the ionizing photons escape from these galaxies? Because as you know from your simulations, these galaxies are very gas rich. So if you produce photons inside the galaxy, they have to be able to escape somehow before, and just not just being absorbed inside the galaxy. And then, what mechanisms allow this escape, etc. And then, as you see, there are many questions. And as I'll show you empirically, we're trying to approach some of these questions. And I think we have some ideas on that also from observations. So the evidence, to say why galaxies should be probably are the most dominant contributors to cosmic reionization basically comes from this kind of picture here, which is what we call the luminosity function of galaxies. The UV luminosity function basically gives you just a number of galaxies per unit volume and per unit magnitude. And as you probably know, these are the faint galaxies, these are the bright galaxies. And what these observations show is that, the fainter you look, the more galaxies there are. So there are large numbers of faint galaxies. These are the number counts. We don't know yet, whether this turns down or so, if there's some kind of fundamental limit or minimum mass needed for a galaxy. We hope that we'll be able to answer that with James Webb. But already, if you assume that these galaxies here, which you observe in the UV, suppose that 10% typically of the ionizing photons which the stars in these galaxies produce, they could escape, then actually just by summing up all these UV photons from this population, you can already see that's down to just the number of the galaxies we see already with Hubble. You can roughly produce enough photons to reionize the universe. So, we don't have a problems in terms of energy or in numbers, but it's of course not a proof that these are the drivers. But this is just an argument to say why we think they are the dominant. And in fact, among the people studying the contribution of galaxies, there's the big debate, is it low mass galaxies, high mass galaxies mostly? We don't know yet. But, on average, we think we would need a fraction of the order of 10 to 20% of ionizing photons to explain it. And I think what is, maybe 10, 20 years ago, people on the observational side were mostly focused on trying to find, galaxies actually. Are there actually galaxies? whose ionizing photons escape and where roughly 10 or 20% escape. Because if you postulate that's what you need, then you have to find these objects. So there has been a lot of searches going on for a long time, and it has been very difficult. But as I will show you, basically in the last 10 years, there's been really drastically a change. And I think we are now at the stage, that we know how to identify these sources, and we can study these properties, and we can start to make up statistics. So we don't have the problem anymore to find such galaxies. And basically, in doing this game, what we have to do, or the one way to see or to quantify things, is the following. If you want to compute the total ionizing photon production of stars on a cosmological volume, what you can do is write it as a product of three quantities. One is the UV luminosity density, which is what I just showed you before in this UV luminosity function. And then if you know that at a given UV luminosity, or on average, if you know how many ionizing photons are produced per UV luminosity, and if you know what fraction of these photons escape, then you can compute the ionizing photon density. And if that is sufficient to provide to reionize the universe, then we are happy. So observationally, these are the two numbers we're trying to measure: ionizing photon escape fraction and the photon production. And as I said, I think we have really made progress. The community has really made progress in the last less than 10 years, maybe 6 years. Because, for example, even papers in 2017 initially, this was the best things we could actually report at that time. And as you can see, this is showing the escape fraction as a function of magnitude of galaxies. There were mostly upper limits. There were not really, we did not have really significant detections. And now we are here. We have a point here. Every point here, except for some of those arrows down here, are detections of Lyman continuum. So we have more than 100 points, 100 detections at low and high Z in individual galaxies and in stacks, and we can start to study the properties of these galaxies. So just to show you an example, how does a Lyman continuum emitting galaxy look? There are a few nice individual objects which are interesting to study. For example, one is the galaxy named IN2, discovered by Eros van Zella. And here you can see different observations we have of this galaxy. So there's plenty of data, images. Here is an image in the Lyman continuum, so showing radiation at less than 900 angstroms. That's the image of the galaxy at longer wavelengths. You can study its spectrum, its morphology, etc. And when you do that, what you can see that this galaxy is a somewhat low metallicity, low mass galaxy, and it has very strong lines, which show that the interstellar medium is highly excited. Other examples of Lyman continuum emitting galaxies are this. This is a strongly lensed galaxy, which was discovered relatively recently. And you can see here that it's stretched, and you can resolve it into multiple images of always the same stellar cluster. These are 6 multiple images of the same object cluster in this galaxy. And there are actually, I think, 11 or 12 counter images of this. And this is an image in the Lyman continuum. So you directly see Lyman continuum radiation. It's very spectacular and a nice example which allows us to study a lot of details about this cluster, how it escapes, the radiation escapes, etc. These are other examples showing more statistical samples of hundreds of galaxies, which have been studied for a long time by the Stadel group in California and by others using VMOS, where we know with spectroscopy, we have been able to identify Lyman continuum emitters. And this you can recognize here. These are UV spectra, the Lyman limit. So, the energy limit, the 13.6 electron we needed to ionize hydrogen is here. So you can see that you can find in stacks, so average spectra, you can find objects which have some flux, which is escaping here. And from that, compared to the intrinsic UV production, you can determine escape fractions. So we have now some significant amount of data available at high Z, and what I want to talk about now is, first of all, what we have learned from low Z equivalents of objects, which we discovered actually starting in 2016. So indeed, with HST, we were very happy to discover in 2016 basically the first Lyman Continuum emitting galaxies, which had a significant escape fraction of the order of 7%. This is just an illustration that was the, these are very compact galaxies we looked at. I will tell more about it. This is the kind of spectrum you obtain. And again, you can measure here flux in the Lyman Continuum, a very clear detection. Since then, actually, things have moved pretty fast. And we have obtained now a rich data set of Lyman Continuum observations of more than 100 galaxies with HST, so with the COS spectrograph. We have a lot of spectroscopy from the UV to the optical. We have different imaging and so on. It really allows us to study a lot of aspects, and I will just illustrate some of these in the next part of my talk. So, but now one important aspect when we talk about sources of cosmic reionization is related to what we call indirect indicators of Lyman Continuum. You probably all know, or it's kind of natural from what I explained already, that we can try to observe and take an image of the Lyman Continuum of a galaxy here and there, or take a spectrum. But what we also know is that if we want ultimately to identify galaxies in the epoch of reionization, so above redshift 6, we will not be able to do that. We will not be able to take an image in the Lyman Continuum or a spectrum because the photons which escape these galaxies, they are used to reionize the universe, so they will never reach us. So the intergalactic medium is not transparent. So if we want to count the galaxies and say, this one is one which is a Lyman Continuum emitter, and this one is not at high redshifts, we need to be able to recognize them. So we need to have indirect indicators because we cannot look at them directly. And yes, this is basically due, to the transmission of the IgM, which decreases very rapidly. And of course, that allows us to identify quasars and the Lyman, the IgM absorption trough and so on. So, when we started this observational program around 2015, what were actually the proposed indirect indicators available in the literature? There were actually 3, basically. Namely, one was suggesting that a particular ratio of oxygen emission lines in the optical could be an indication. Another was that Lyman-alpha line, and another was that UV absorption lines could show us which galaxies would be Lyman Continuum emitters. The basic idea behind that are quite simple. Suppose that you have a galaxy where the interstellar medium is schematically, is just like that. It has a few clouds where most of the gas is sitting, but between the clouds there are empty channels, or channels with a very low column density. In this case, you can easily see that Lyman Continuum radiation will be absorbed in these clumps, but in between there, they can escape. So a clumpy structure could allow the escape. Now you could have dust also in these galaxies. If you can have a foreground screen, which may attenuate some of the radiation, or the dust could be inside the cloud, in the clumps. So, with this kind of clumpy, or what we call picket fence geometry, you can imagine very easily that Lyman Continuum photons can escape. And observationally, that will translate into weak absorption lines like this here. If you study lines which are actually intrinsically saturated, so which for a very low column density of metals are basically absorbing all the radiation, then you get this kind of spectrum here. You get no flux at the bottom of an absorption line because this line is saturated and it absorbs all the radiation. But if you look at the same line in a galaxy where the geometry is clumpy, you will have some UV radiation which goes directly to the observer, and this line will be, even if it's intrinsically saturated, so in the clumps, it will not be. The flux, the cover, what we call, the residual flux of the line will not be 0. So that is a simple way we think we can recognize and we can determine this geometrical covering factor, or the clumpiness of the galaxy. So that was proposed, to try and find Lyman Continuum emitters, and as I will show later, it turns out that indeed it works. The second probe, which was proposed from radiation transfer simulations by my colleague Anwar Ham, was that the Lyman-alpha profile in such clumpy objects, or in objects where you have either channels or which are completely ionized, that actually the Lyman-alpha profile would show distinct features, either a strong Lyman-alpha centered at centered at 0, or double-peaked Lyman-alpha profile, which indicate some scattering, but not too much scattering, depending on how much gas there is in the channels and so on. So that was an indirect indicator which was proposed. And then other people had proposed also that, as I mentioned, that the ratio of oxygen 3 to oxygen 2 lines could be peculiar in galaxies where the ionizing photon escapes. The physics behind that is very simple. If you assume that you describe the whole galaxy by just one spherical H2 region, which is of course very naive, then you would have this kind of structure here. You have the inner part where you have, doubly ionized oxygen, and then you have singly ionized oxygen, and here you produce O3 lines, here O2, and that gives you a certain ratio of O3 to O2. But now if this galaxy, if it has a strong production of ionizing photons, or if it lacks gas in the outer parts, so that the ionizing photons can escape, you're somehow losing the outer parts of a normal H2 region, where you have always a Strömgren radius and where things recombine. And if you lose the outer parts of the galaxy, then it means simply that you're missing O2, and therefore the ratio of O3 to O2 will increase. Very naive picture, but it's something you can test, and that's indeed what we did. And so we went with my colleague Yuri Isotov, who's an expert on compact galaxies in the nearby universe and in spectroscopy. We went and selected galaxies with very high O3 to O2 ratios. We selected galaxies also which are very compact, because we wanted them to be sufficiently compact that we can integrate the whole spectrum and measure the total spectrum with the Hubble Space Telescope with COS. And yes, basically these are, and then there was a technical constraint also that we need to go to redshift 0.3 at least, because at lower redshifts, HST is not sensitive at these wavelengths. So what we did is indeed we observed 5 galaxies, and on the very first program, these are the unspectacular images of those. By selection, they were compact. We made sure that they don't contain AGN according to classical diagnostics. This is a first image we obtained with the Hubble, so it's really compact, but it shows some structure. And then, as I said, we obtained this kind of spectra, which was really amazing. Just 5 objects, and every object, it turned out, in fact, had Lyman Continuum escape. Before, people were searching were spending ages and hours of Hubble time and did not find any. So at the beginning, we got a sample of 11 objects with a lot of with 100% Lyman Continuum escape, and we started to see some kind of trends that the escape fraction was indeed maybe increasing with O3 to O2 and so on. So, but it started to be very promising. We also obtained very detailed Lyman-alpha line profiles to compare with the predictions from the radiation transfer model. And lo and behold, it turned out that all the profiles, they actually looked double-peaked or triple-peaked. So similar to what my colleague actually predicted. And we found a very nice correlation, which by now is one of the best indirect indicators, namely that's the escape fraction of ionizing photons correlates with the separation of these 2 peaks of the Lyman-alpha trough. And you can understand that basically because the peaks are more and more separated if there's more and more scattering in the galaxy. And if you increase the column density of hydrogen, you have more and more scattering and therefore less photons get out. So that's why qualitatively you expect this kind of behavior. And yes, so these were nice confirmations, that these proposed indirect indicators could pinpoint Lyman Continuum emitting galaxies. So now we wanted to check also and to look at the absorption line properties, which was the third indicator. And we studied that, and we wanted to determine this covering fraction and try to measure column densities and so on, which you can do from absorption lines. So basically we work with this kind of picket fence models. We study a lot of different absorption lines, and depending on the geometry and where you put dust, you can have different equations for the absorption lines. And then you can take spectra, look at them, and see whether empirically already you can see very quickly that, for example, objects like that here, you see they have completely saturated lines, where the flux is at 0. And this is an object where there is no Lyman Continuum escape. If you look at Lyman Continuum emitters, that's the way they look. The lines which you expect to be saturated, they have a flux which is not 0. And that shows you that basically, very easily here that I don't know, 20% of the UV flux is escaping the galaxy directly. So it tells you quite straightforward way that, you know, we have this picket fence or these holes or channels. Okay, you can be a little bit more quantitative, and you can measure, you know, the residual fluxes. And now, after a few years, in the recent paper from my PhD student Alberto Saldaña-Lopez, we have, as I said, roughly 100 measurements, and you know, we can very nicely see that there is a clear correlation between the escape fraction and this residual flux in the lines, which really excludes, you know, the option that most of the for most of the galaxies, that they are completely ionized to different degrees. It means that there are regions, you know, where you have where you have dense clumps, where you have also neutral gas, but there are regions which are either empty or of a very low count density, and through which the photons can escape. Actually, I did not check at all when I started, and I forgot to ask you how long I'm supposed to. Can you just quickly? How much? Okay, good. No, just to make sure. And if you have questions, I don't know what's the habit here. You may also interrupt, of course.
So these are all examples of lower redshift.
Yes, the large samples are at redshift 0.3 to 0.4 essentially.
Is diagnostic.
Yes, we're using them to test the physics and to calibrate them. Yes, exactly.
So, what's the parameter that quantifies the amount of dyes that, you know, goes what you call the direct starlight with Lyman C?
In the simple geometry, the main parameter which governs it is the covering fraction. So how much? Yes. Exactly. But we think there's also effect of dust. So there is some absorption of dust also, and there is some gas present in these channels, and that also attenuates a little bit the radiation. But one of the main factors is the covering factor. And that's in fact what I'm going to show you here. So, you know, if you have these measurements, you can say from a simple analytic equations in this geometrical case, you can actually predict, you can write down what is the escape fraction of ionizing photons, depending if you have a uniform dust screen or a clump. And here you see which are the main parameters is the covering fraction. So, and the second parameter is the attenuation of the radiation at these wavelengths. So that's what we expect with this naive geometrical model. And then, in fact, in the galaxies where we have all these measurements, we can test, does this work? So can we predict analytically with the simple equations and with two measurements, the covering factor and the dust attenuation, can we predict actually the Lyman continuum escape? And that's exactly what we did here in our initial work and now in Alberto's PhD thesis. And you see that, of course, there is some scatter, but, you know, we have significant correlation between the predicted escape fraction just from a measurement without looking at the Lyman continuum, just the absorption lines and the UV attenuation and the measured one. So, you know, this validates to zeroth order or to first order this simple diagnostic. And in fact, we are also working, and there's on comparing this in simulations. Maybe you have seen the work from Valentin Mauerhofer, PhD student of Anverham, who is doing these things in mock simulations, and he finds essentially similar trends, which confirm, you know, this. So it means that in more realistic simulations, you know, we validate also these behaviors here, which are found empirically and which we can understand from this naive picket fence model. So in a nutshell, I think where we are is, you know, we have from these first observations, we have kind of validated quantitatively or semi-quantitatively 3 indirect probes of Lyman continuum, namely the usage of this O3 to O2 ratio, the profile of Lyman-alpha, and the use of the UV absorption lines. So in principle, we could say, you know, they work on redshift 0.3. So let's, on one hand, maybe we want to test them, you know, in other objects at higher redshifts, and then, you know, we can go and measure those quantities with the James Webb, with ELTs and so on, and we can determine without looking at the Lyman continuum the escape fractions. So we should be ready. But okay, well, of course, we did not stop here. And before that, I want to tell you now, what did we learn? Now that we know how to identify galaxies, what are these galaxies and what are the properties of the galaxies which, emit Lyman continuum photons? So, and in a nutshell, the properties we found for the strong leakers, I'm not talking about the whole population. So for the ones which have escape fractions above 10%, for example, because we found, for example, objects, I did not say this, which have escape fractions of 70%. 70% of ionizing photons escape. Recently, with a colleague of mine in Geneva, we found the redshift 3 galaxies, which we think the escape fraction is around 90%. It's a monster UV bright galaxies, has extremely weak emission lines, and it's booming in the Lyman continuum. So what are the properties or physical properties of these Lyman continuum emitters we found at low redshifts? They are compact, the strong objects, you can say by selection, but as I will show you later, if you widen your selection, you still find that compact objects, that strong leakers are essentially found among compact objects. We can study because they are at low Z, we can study all their physical properties. We can determine stellar masses, abundances, and whatnot, star formation rates, extinction, attenuation law, and so on. And what we typically find is that the stellar population in these galaxies are young. They are dominated by young stars, and it's difficult to find actually and to quantify the underlying old population. We don't know how much. Their masses are relatively low, of the order of 10 to the 9 or lower. Now we have some which go down to 10 to the 7 solar mass. They have, star formation rates which follow the usual relations, but they have high specific star formation rates. They are low metallicity, but not extremely low metallicity, and they are dust poor overall. We have, yeah?
Samples, you have 5 galaxies, you get a handful of galaxies
that
you found.
They are very rare. I have a slide which will show that a little bit. We can actually not give exact numbers because the LzLCS is incomplete. It's difficult to determine volumes, but they are extremely rare at low redshifts. We basically handpick them, but I will show you in a minute a slide on that. So what we also did, I told you what we want to measure is the escape fraction of ionizing photons, but we want to know also how many ionizing photons they produce in the beginning, because the product of the two is how many ionizing photons will reach the IGM, right? And we did that this is the first measure we did, but we have now larger samples. And what we found is that on average, these galaxies, they produce also a little bit more ionizing photons, roughly 2 times more or so than what was canonically assumed before. And it simply relates to the fact that they are relatively young populations, and at younger ages, you produce more ionizing photons per UV luminosity. Yes, there was a question in the back, or?
This distinguishes these galaxies with high escape fraction and this Lyman continuum from the others? Are they like gas? Gas?
What you're saying related to the gas fraction, or?
How does these galaxies gas or
in fact, about the gas, it's difficult to say right now. I think the overall properties, what we conclude, how should I say this? If you look at the typical galaxy in the Sloan, our galaxies are very different, and they are characterized by selection, by compactness, very high star formation rates, very strong emission lines, and high specific star formation rates, so high SFR per stellar mass. For example, you can quantify this in this kind of picture here, which shows, if you look at the Sloan and other surveys of star-forming galaxies in a certain mass interval, you can measure the strengths of emission lines here of H beta and O3 and here of O2. And you can see, in fact, that this, the average population has a certain but relatively low strength of emission lines, because, it includes your average spiral galaxy, and then it includes more dwarfish galaxies, and then it includes some bursty galaxies and some rare green pea-like galaxies like the ones we are studying here. But so that is what you see in the low redshift universe. And now when you go to higher and higher redshift and you do that in the same mass interval, you see that the equivalent width of galaxies increases when we go back in time. And in fact, what is the equivalent width of our galaxies? It's here in this plot. It's around 1,000. So you see, but these galaxies are sitting at redshift 0.3, so they're sitting here. So they are really in the tail of the normal galaxy populations at low Z. There are very few of them. But what is interesting is in fact that all the properties we can measure for these galaxies, and we can measure quite a lot because they are nearby. So all the properties, the empirical properties, the stellar masses, the sizes, the star formation rates per area, and the high gas densities, all those properties, they compare very well. They agree very well with the properties the typical redshift 6 or 7 galaxy has. You know, so they are weird. They are weirdos. They are outliers in the low Z universe, but their properties turn out to be, at least to our current knowledge, very similar to the properties of the average galaxy at redshift 6 or 7. And that's why we call them analogs of the sources of cosmic reionization. And now you have to explain, of course, why is that possible still at redshift 0.3, you know, that this happens and so on. And to come back to your question of the amount of gas, in fact, we don't know the gas fraction in these galaxies. We tried to detect gas, so cold molecular gas with ALMA, we did not find any. All we can say is that to the limits we have right now, but we have not published these upper limits yet, these galaxies contain much less gas than a normal dwarf galaxies at low redshift. But we don't know, for example, you know, what makes this galaxy burst, because they are extremely bursty now. And they don't contain a strong old underlying population. We don't know what makes them. And okay, so you see there's still a lot of questions, but empirically we can say they are excellent analogs of the high Z galaxies. And I think this is another slide, you know, to show now that we start to get more data with James Webb. For example, this is a paper which came out just at the beginning of this week or last Friday. Now we are able with James Webb to identify and to measure direct spectroscopy of galaxies. Here it's at around redshift 6.7. You can take spectra, and this is a Grism spectrum, for example, showing the oxygen 3 emission lines and H beta, and you can measure the equivalent widths of these lines. And in fact, here you have the measurements. So you see actually that these redshift 6 galaxies, which our colleague Yorit Mati, who was quite some time at ETHZ, maybe some of you met him, these equivalent widths here, they are, you know, between 1,000 and 3,000. It's exactly the same equivalent widths we're measuring at redshift 0.3 in these strong leakers. You know, it's again a confirmation that by all the properties we can measure, there are very good analogs. And now, yes, let me move ahead. So what are, you know, if we try to summarize things about the ionizing photon production, what do we think? What is the global picture? We think, in fact, that first of all, the ionizing photon production depends on the strength of the emission lines, which we understand theoretically it's mostly related to age of the burst. And we think that, you know, because the average equivalent widths of galaxies increases with redshift, that the ionizing photon production also increases with redshift. So in a nutshell, you know, in the early universe, the ionizing photon production will be strong, and it will be stronger in faint galaxies. And among those, in fact, we find a lot of Lyman Continuum emitters. So, you know, it shows that, roughly speaking, we should really not have a problem to explain cosmic reionization. But now let me briefly back this up a little bit with more statistical results. You know, I initially said from a small sample, but I want to mention briefly this HST program, which we recently completed, the low Z Lyman Continuum survey, which brought us essentially to approximately 90 galaxies with measurements in the Lyman Continuum. I will not have time to discuss this in detail, but the idea of this proposal was, of this program, was to say, you know, initially we selected some very peculiar objects with high O3 but what about the more general properties of Lyman Continuum escape? You know, if we relax the assumptions, if we move away from the most compact, so, you know, how does the escape change with galaxy properties? And for that, we made this survey here, you know, moving away widening the range of physical parameters. And we've managed indeed to obtain a significant number of detections, roughly 40 to 50 detections, depending on where you set your thresholds. You know, we have a lot of detections and upper limits. We have escape fractions, as I said, in some objects, which can reach 70, 80%, and we have upper limits, which can go down to a few percent. And from this kind of paper, what we found is basically, you know, we've confirmed the trends we found before, that on average, with increasing O3 to O2 ratio, the escape fraction increases. But what we can also say to first order now is, you know, what fraction of galaxies at a given O3 to O2 are Lyman continuum emitters, and that is what is plotted here. And here you can see that indeed, you know, if you go to objects which have a very high excitation, the chance that it is a Lyman continuum emitter, at least at low redshifts, starts to be pretty high. We have also interesting correlations, and I think this is very important in the context with simulations, is namely that the escape fraction depends strongly on the compactness of the object, in the sense that if the star formation rate per unit area increases, then the escape fraction increases. That is what this factor here, what this plot here shows. And again, the detection fraction, you know, strongly depends on that. So we think that, you know, this must be telling us something about the physics which allows the escape of ionizing photons. And I think it's also something I would like to discuss with some of you. For now, we don't have models which allow to explain this really. I think, you know, it's related to some efficiency in driving holes in the interstellar medium and feedback and so on. But maybe this is something some of you simulators will pick up and explain. We have other correlations with dust, etc. So to summarize, you know, what we have learned about the physical properties of the Lyman continuum emitters is shown here in these figures. First of all, I would like to say, you know, we found, first of all, strong Lyman continuum emitters, they exist at low redshifts. They must also exist at intermediate redshift. We have also found weak Lyman continuum objects, and we also found some bright objects. So we don't know exactly how much the weak, the low mass galaxies and the bright contribute. This is still a little bit an open debate. But what seems to be clear is that if you look at the strongest, so the most efficient Lyman continuum emitters, they are compact objects with high star formation surface density, as I said, etc. The low mass, low metallicity, and strong emission lines. And as we already said, and these objects are, to the best of our knowledge, good analogs of the typical object at high Z. In passing, you know, in gathering all this data, in fact, we have been able to come up with many additional indirect indicators. I just had time to discuss these 3 indicators here, Lyman-alpha, UV absorption lines, and high O3 to O2. But in the meantime, actually, we find other empirical indicators for Lyman continuum escape, which is really opening the game and, you know, allowing us to address them observationally quite nicely and providing new insight. And for that, I think we will be moving on pretty soon with the James Webb, with different programs. One of them is the program I'm leading, and which will start to observe redshift 3 galaxies, which are known Lyman continuum emitters. So building on the work where people have gathered 20s, 50s of redshift 3 Lyman continuum emitters over time. We're going to look at these galaxies in the rest frame optical. So in fact, we're going to get exactly the same data as we have now at redshift 0.3. We're going to get for the first time with James Webb at redshift 3. Of course, these are, you know, epochs which are separated. One is 2 gigayears after the Big Bang, and the other is 10 gigayears after the Big Bang. So we will be able to test the exact same list of indirect indicators at redshift 3 and see if there is any difference, you know, and of course, we will be able to measure also properties of the radiation field of the interstellar medium, and we'll see, you know, how do some of these properties change between low Z analogs and galaxies at redshift 3. Maybe they don't change, we don't know. And of course, with this baseline, we will be as close as we can to the epoch of ionization, because doing the same things at higher redshift will not be possible anymore because the Lyman continuum becomes opaque. Right, so that's what we're going to do with the James Webb. And as I said, yes, the idea is, of course, to get to probe this baseline in time, you know, between 2 gigayears after the Big Bang and 10 gigayears after the Big Bang. And then we should be best equipped to observe and to interpret observations in the epoch of ionization. And in fact, this summer, we've seen already that the James Webb can produce amazing spectra. You know, this is a spectrum which we extracted from the observations shown in the first press release of JWST in the middle of July. When we saw this spectrum, we did not actually expect to see any spectra in the first press release. When you show the spectrum, it's like, ah, okay, it's exactly like our galaxy at redshift 0.3. It's amazing. It just looks exactly the same way. Here you have a spectrum of a low silica, and that's a galaxy, a more or less randomly chosen galaxy at redshift 8. They look the same. It's amazing. And you can do all the physics. You can measure directly metallicities. With this line here, you can determine the electron temperature. You can directly measure abundances, line ratios, etc. In fact, James Webb here has just released 3 spectra of redshift 8 galaxies. All the line ratios we can measure, they basically look exactly as our low-Z analogs. So it's really quite spectacular, and you know, there will be tons and hundreds of spectra taken with the James Webb in the future, so it will be very exciting. Now I have a last part on the feedback, and depending on how much time I can make it short or not, 5 minutes. I think if I can do everything, or I'm sorry, I did not properly. Okay, let me give you quickly that, because it's also what connects, what brings the questions for you. So among the lessons we learned from these low redshift analogs is also, as I already mentioned, is how the ionizing photons can escape. It's a geometrical effect, and it tells us that there are, you know, clumpy structures or holes and low density channels. That is pretty clear. And it also means that we need to change actually our tools. We cannot model the galaxies anymore as a simple H2 region. So we need to combine, we need to superpose at least the 2 different phases. And that means that, you know, to interpret them, we need to include more complex models. But the more important question, I guess, is, you know, what causes actually this structure, and how does it work, you know, and can we explain the correlations of this escape fraction with the star formation intensity and the compactness and so on. And that I think must be, you know, related to what can cause these channels, and, you know, what feedback or what is the reason or what is the mechanism causing this. And of course, you know, we are always wondering, how does it happen? Is it supernova feedback, which everybody puts in simulation? But I know you're putting more feedbacks. Other people speculate now about more crazy feedback effects. Some people say, in some objects there is a possible link between the presence of ultraluminous X-ray sources and Lyman Continuum escape. So you see all kinds of you know, interesting speculations coming up. But I think what I want to say is that in fact, so far we have not been able to find any evidence for supernova feedback in the strong Lyman Continuum emitters. We are really trying to do it. And but I cannot report any significant results where we could actually, you know, say it must be supernova which caused this. And the main evidence for or against supernova is the following. Basically, as I mentioned before, when we look at the strong leakers, they are dominated by a very young population. And in fact, and when I mean young, I mean 3 to 5 million years. We have a very hard time to find any indication for older stars. Now, if the bulk of the population is 3 million years, suppose, you know, at 3 million years, that's where you start to get the first supernova. But it means that, you know, if that's all there is in the galaxy, there has not been many supernovae before. Okay, we cannot give age estimates very accurately, and, you know, not all the stars will be born at the same time in the galaxy. But anyway, it's, you know, it's a bit problem. Then there are people in studying spectroscopy and line kinematics and so on, who suggest that actually in very compact galaxies, you could have suppression of super winds, so the adiabatically driven winds from different kinematics. And they debate, you know, whether this would be rather momentum-driven winds and so on. There is a whole literature on that, and I can give you more references on that. We are observing actually with high resolution the kinematics of the ionized gas, and we find very fast outflows which some people interpret also as radiation-driven outflows. And then I have also some information from radio. So this is just to show in a nutshell. It's not yet published, but we have a lot of data from that, which shows, and if you look at these emission lines in more detail, you can actually see that these lines are asymmetric. Here you have the oxygen 3 line and the H-beta line. And there is a component which extends in the strong leakers, which extends to the blue and which is very broad. And if you measure, actually, you can see here, there is emission going out to very high velocities. And these are the typical velocities we can get. So we can find ionized gas at velocities up to 1,000 kilometers per second in these objects. And it's asymmetric, so it's probably telling us, that this is not a symmetric outflow, but it looks like to me, there is a channel, and through this channel, the gas is just speeding out at 1,000 kilometers per second. So it's kind of a free flow, What drives it and what makes these channels still, I don't know. If you can make them a supernova, then we would like to see supernovae. Where do we usually search for supernovae? One way is to look at the radio, because supernovae, they usually drive non-thermal radio emission, synchrotron emission through complicated mechanisms in the interstellar medium. But when we start to observe radio in the radio continuum, the Lyman Continuum emitters and others, we have a hard time to find a lot of non-thermal emission. And in fact, if one way to show this is in this very preliminary work, which my postdoc, Astrophysics postdoc, Omkar Bait, is working on right now, we find actually, that if you look at strong leakers, there seem to be more in this corner here, which is dominated by thermal spectra. So, we still need to work on this more precisely, and we can also measure the fraction of flux, which is thermal and non-thermal. And it just seems that the strongest leakers, we do not see any significant contribution from non-thermal emission. If that's true, and if that tells us that there are not many supernovae or no supernovae, then yeah, maybe that's telling us something about feedback. So as I said, it's still preliminary and we don't know. But so far, I think when we can say that we have not found any evidence yet for supernova feedback causing these channels. And then, of course, the question is, if it's not supernova, if we will converge to that, what is it, right? I think I would like to ask you, what is it? Some people say radiation-driven or whatever, but there's definitely much more work needed. But for example, one implication is also, regarding this kind of conclusion, which, for example, in this Rostal paper here, maybe some of you have followed it, they have done cosmological radiation transfer simulations with relatively high resolution, and they, so from ab initio with their feedback, they predict escape, ionizing photons, and then they compute the ionized fraction of the universe as a function of time. And this is what they obtained with their standard physics and when they use normal stars, single stars. So they found a result like that. Well, the reionization does not properly start until redshift 6. So they say, okay, maybe we need binary stars. It tells us that we need binary stars. They made simulations with binary stars. It produces this result, and then they say, we need binaries to reionize the universe. But what does it mean? Or what does it depend on? It depends on the fact, why do they need binary stars? Because in this type of simulations, the only way or the only time when the ionizing photons can escape is after supernova have occurred and have cleared the path. But the typical supernova occurs after 10 million years, the average one. And at 10 million years, you don't have massive stars anymore, normal massive stars. They end their life, the stars which produce ionizing photons, they live less than 10 million years. So basically you have a problem of timing, right? When the supernova has cleared the ISM, there are not many ionizing stars left anymore. So you say, okay, if we want to reionize the universe at that time with supernovae, then we need longer lived stars which can produce ionizing photons. And then those you can find in binary systems. But maybe our observations are showing that this is not true. The ionizing photons, they get out much more early. So, I think just to say, I'm sure it will, for people working on simulations, I think there's a lot of things to explore. It would be really fun and really interesting. And I think I should stop here now. Sorry for taking all the time. So I'll just summarize. Yes, I think I don't need to go through the summary slide again. Thanks a lot.